Imagine a world governed by different rules, the quantum realm, where energy, light, and matter behave unexpectedly. Here, everyday intuition breaks down, replaced by quantum mechanics. Energy exists in discrete packets called quanta, and particles can be in multiple states at once. Observation influences the observed. Explore wave-particle duality and quantum entanglement. Join me to unlock the secrets of the ultra-small. Quantum physics can seem strange and counterintuitive. Energy exists in discrete packets called quanta. Imagine a staircase where you can only step on specific steps. Particles, like electrons, exhibit wave-particle duality. Light acts like both a wave and a particle. Measurement affects quantum systems. A particle exists in a superposition of states. Schrödinger's cat illustrates this concept. Our journey into the quantum world begins with Max Planck, a German physicist who, in 1900, unknowingly ignited a scientific revolution. Planck was wrestling with a problem that had baffled physicists for years, the blackbody radiation problem. Classical physics failed to explain the observed spectrum of light emitted by a heated object, known as a blackbody. Planck's groundbreaking solution was to propose that energy was not emitted continuously but in discrete packets, or quanta. He formulated the famous equation E equals sine hf, where E is energy, F is frequency, and H is a fundamental constant now known as Planck's constant. This revolutionary idea, initially met with skepticism, laid the foundation for quantum theory. Planck's discovery shattered the classical view of continuous energy and introduced the concept of quantization, a cornerstone of modern physics. His work, recognized with the Nobel Prize in Physics in 1918, opened the door to a new era of scientific understanding. 5 years after Planck's groundbreaking work, a young Albert Einstein would further illuminate the quantum world. In 1905, Einstein published his groundbreaking paper on the photoelectric effect, a phenomenon where light shining on a metal surface dislodges electrons. The peculiar aspect was that the energy of the ejected electrons depended solely on the frequency of the light, not its intensity. Einstein, drawing upon Planck's idea of energy quanta, proposed that light itself was quantized, consisting of discrete packets of energy called photons. This revolutionary concept explained the photoelectric effect perfectly. Light, Einstein argued, could behave not just as a wave but also as a stream of particles, each carrying a specific amount of energy. Einstein's work, earning him the 1921 Nobel Prize in Physics, solidified the concept of light quanta and propelled the development of quantum theory. It also highlighted the dual nature of light, a concept that would become central to understanding the quantum world. One of the most mind-bending concepts in quantum physics is wave-particle duality. This principle states that particles like electrons and photons can exhibit both wave-like and particle-like properties. The classic example is the double-slit experiment. When particles are fired at a barrier with two slits, they create an interference pattern on the screen behind it, much like waves do. This suggests that the particles are behaving like waves, spreading out and interfering with each other. However, if we try to determine which slit each particle goes through, the interference pattern disappears, and the particles hit the screen as discrete points like tiny bullets. The act of observation seems to collapse the wave function, forcing the particle to choose a definite path. Wave-particle duality challenges our classical intuition, where an object is either a wave or a particle, but not both. It highlights the probabilistic nature of quantum mechanics, where we can only predict the likelihood of finding a particle in a particular state or location. In the early 20th century, physicists were grappling with the structure of the atom. The prevailing model, proposed by Ernest Rutherford, depicted electrons orbiting the nucleus like planets around the sun. However, classical physics predicted that these orbiting electrons would continuously emit radiation, lose energy, and spiral into the nucleus, rendering the atom unstable. Niels Bohr, a Danish physicist, revolutionized atomic theory in 1913 by incorporating quantum principles into Rutherford's model. Bohr proposed that electrons could only occupy specific discrete energy levels within the atom. These quantized energy levels, represented as orbits, prevented the electrons from spiraling into the nucleus. Electrons could jump between these energy levels by absorbing or emitting photons of specific energies, corresponding to the energy difference between the levels. Bohr's model, while a significant leap forward, wasn't perfect. It provided a framework for understanding atomic spectra and laid the groundwork for the development of full-fledged quantum mechanics. In 1927, Werner Heisenberg, a German physicist, introduced a revolutionary concept that shook the foundations of classical physics: the uncertainty principle. This principle states that there are fundamental limits to how precisely we can simultaneously know certain pairs of physical properties of a particle. The most famous example is the position and momentum of a particle. Heisenberg's uncertainty principle dictates that the more precisely we measure a particle's position, the less precisely we can know its momentum, and vice versa. This uncertainty isn't due to limitations in our measuring instruments, but is an inherent property of quantum systems. Imagine trying to pinpoint the exact location and speed of a fast-moving tiny particle like an electron. The act of measuring its position inevitably disturbs its momentum, and vice versa. Heisenberg's uncertainty principle highlights the probabilistic nature of quantum mechanics, where our knowledge of a particle's state is always limited by a fundamental fuzziness. Erwin Schrödinger, an Austrian physicist, devised a thought experiment in 1935 that remains one of the most famous and perplexing illustrations of quantum mechanics: Schrödinger's cat. This thought experiment highlights the concept of superposition, where a quantum system exists in multiple states simultaneously until measured. Imagine a cat sealed inside a box with a device that has a 50% chance of releasing a lethal poison. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states, both alive and dead. Only upon observation does the cat's wave function collapse, forcing it into one definite state. Schrödinger's cat, while a thought experiment, illustrates the counterintuitive nature of superposition and the role of observation in quantum mechanics. It sparks debates about the interpretation of quantum mechanics and the nature of reality itself. One of the most baffling and intriguing phenomena in quantum physics is quantum entanglement. This phenomenon involves two or more particles becoming linked, even when separated by vast distances. Imagine two particles, entangled in a way that their properties are correlated. If we measure the state of one particle, we instantly know the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, challenged the classical notion of locality, where information cannot travel faster than the speed of light. Quantum entanglement has profound implications for our understanding of the universe. It suggests a deeper interconnectedness between quantum systems, challenging our classical intuitions about space and time. Entanglement is also a key resource for quantum technologies, such as quantum computing and quantum cryptography. Quantum physics, once a realm of theoretical exploration, is now deeply embedded in our technological world. From lasers and transistors to medical imaging and GPS, our lives are profoundly influenced by technologies that rely on quantum principles. Lasers, for instance, harness the quantum properties of light to produce highly focused beams with applications in telecommunications, medicine, and entertainment. Transistors, the building blocks of modern electronics, rely on the quantum behavior of electrons in semiconductors. Medical imaging techniques, such as MRI and PET scans, exploit the quantum properties of atomic nuclei to provide detailed images of the human body. GPS navigation systems rely on atomic clocks, which utilize the precise frequencies of atomic transitions governed by quantum mechanics to provide accurate timekeeping and location data. These are just a few examples of how quantum physics has revolutionized our technological landscape. As our understanding of the quantum world deepens, we can expect even more transformative technologies to emerge. The quantum realm, with its mind-bending principles and counterintuitive phenomena, holds immense potential for future technologies. Quantum computing, one of the most actively researched areas, promises to revolutionize fields such as medicine, materials science, and artificial intelligence. Quantum computers, leveraging the principles of superposition and entanglement, could solve problems that are intractable for even the most powerful classical computers. This could lead to the development of new drugs, the design of novel materials with unprecedented properties, and the creation of more sophisticated AI systems. Quantum cryptography offers the promise of unbreakable encryption, exploiting the principles of quantum mechanics to secure communications. Quantum sensing, another burgeoning field, explores the use of quantum systems to detect and measure physical quantities with unprecedented precision. This could lead to the development of highly sensitive sensors for medical diagnostics, environmental monitoring, and fundamental research. The future of quantum is bright, promising to unlock new frontiers in science, technology, and our understanding of the universe.